So the problem that we have is that for some combinations of countries and time periods, we have missing values for a number of our variables. And above, what we did is when we took our data frame, we simply dropped all the rows where there was one missing value in that row. Yeah, so we dropped all observations where for one of the variables we actually had a missing value. But that means that for all the other variables there could have been observations, so that's throwing away a lot of information. And therefore we're going to look here at the Bayesian way of dealing with missing data. And the advantage is that that is better than throwing away everything, all observations which have a missing value, and it's also better than the case where we start to interpolate missing values, let's say replacing them by the mean of a variable or something. And the idea here is with Bayesian is that since we're working with distributions anyway, yeah, both for our variables but also for our parameters, we can also deal with missing observations in the same way. That is, we're going to assume that we know the distribution of the variable, and whenever we have a missing observation, we simply draw a value from the distribution of that variable and use it in our estimation technique. We'll come back to that later. In order to do that, the implementation in PyMC3 uses masked arrays. Yeah, so in NumPy we're used to working with arrays, but you can also work with so-called masked arrays. And to give you an idea of what a masked array is, I'm defining one here. So the variable x is not a NumPy array, a simple NumPy array, but it's a NumPy MA for masked array. So it gives a list of observations. So the first observation is 1, the second observation is 2, and the final observation is not a number. Yeah, so that's a missing variable, so to speak. So we don't have the value for the third observation of this variable. So usually when we specify a NumPy array, we have array and then a list. But now there's a second element which is called the mask. And the mask takes two values, either 0 or 1. Yeah, so in Python that means the 0 is false, the 1 is true. And false refers to the fact that there is not a missing observation. Yeah, so missing observation is false, meaning we do have an observation in this position, namely the 1. Similarly here, the second observation is not missing. Yeah, so missing is false, and indeed we have a value here, it's a 2. The third observation is missing, so we have a true here in the mask, and indeed this is a missing observation. Yes, there are two ways in which we can represent x, the x variable that we just defined. One is when we use the compressed method on x. So that's basically sort of the readable format. So if you look at the x in the compressed format, it's simply a normal array. Yeah, so it simply says this array contains the values 1 and 2, and it doesn't bother you with the fact that there is not a number, so as a not observed value in the third position. But if you look at it in the raw format, yeah, so we look at x in the raw format, this is what you get. So first of all, it tells you that it's actually a masked array. It's not just a standard array, it's a masked array. It gives you the data. So the first is 1, the second is 2, which is indeed correct. And then the third here is not a number is represented by these two dashes. And the mask is false because the first one is not missing, so missing is false. The second observation is also false because it's not missing, there is a value here, but the third observation has a true, yeah, because it is missing. Yeah, and it explains to us how internally it deals with this missing observation. It fills in a value which is pretty big. Yeah, so that's how it works internally. We don't need to worry about that. For us, what's important here is that this masked array is a way of dealing with missing observations formally in NumPy. So now we're going to reload our data, and we're going to turn our the variables that we use to explain mortality into these masked arrays. Yeah, so we have our data frame, we read our data file as we did before. Again, I'm using here a dropna function, so we're dropping the non-observables, but we only do this for the subset of treatable mortality. Yeah, so this is the variable that we want to explain. And basically we're going to say that for the variable that we want to explain, we're also only going to look at rows where there is a value of treatable mortality. Yeah, in fact, you don't need to do that because PyMC3 can deal with missing observations for the variable that needs to be explained. But here we do one step at a time, and here we only look at missing observations for the X variables, for the explanatory variables. Yeah, so here we drop all the observations where treatable mortality is missing. Yeah, so we do in place is true. So we're gonna drop a number of observations from our data frame such that each observation at least has an observation for treatable mortality. Each row has a value for treatable mortality. So then as we did above, we're gonna define our income quantiles, and using that we're gonna define our column inequality. Yeah, it's exactly the same equation that we did before, so we don't need to worry about it now. And then we drop the income quantiles because we need them in the data frame. Yeah, just as a reminder, this is our function standardized that we used above. So we take from x, we subtract the mean, and we divide by the standard deviation of x. Yeah, so remember this f is emacs representation of a fancy representation of def, defining a function, and this thing here is return. So above, what we did for all variables, we now actually only have to do for log mortality is to standardize it in this way. Yeah, and we're going to define this dummy variable gender, which is 1 in case of a female observation. Now for our explanatory variables, so our x variables, we need a new function standardized, which will turn the variable into a masked array. Yeah, so we could do this in 2 steps. So first turn them into masked arrays and then standardize them, but actually it's easier to do it in one go. So this new function standardized is basically the same as this function standardized, except that everything happens here in terms of masked arrays and not in standard arrays as we do it here. Yeah, so what happens here is that the function standard MA for masked array takes an array X, and the first step that it does is it turns that array into a masked array. Yeah, so it turns the X, which is a normal numpy array, into an XMA, which stands for masked array. And then we do the operation of subtracting the mean and dividing by the standard deviation. We do this on the masked array. Yeah, so using this new standardization function, which takes care of the masked array feature that we're going to need, I'm standardizing GDP, yeah, where we take the log of GDP per capita, standardize it using masked arrays, and we do the same for inequality, high body mass index, smoking, and binge drinking. Yeah, so all these variables that we used before are now turned into standardized masked arrays. Yeah, above we simply used standardized arrays, now we turn them into standardized masked arrays. And once we use these in our PyMC3 model, we can take account of the fact that we have missing observations for these variables.